Good morning, everyone. We thank the organizer for giving us the opportunity to participate in this workshop. The following work has been carried out together with Professor Ramon Pino, and whose central idea is to provide a fundamental tool to understand the processes of revision of belief, giving a synthetic vision of the different representation theorems for this process of change. Let's start with the revision of belief. The objective of the revision of belief is to understand how to integrate new information into a corpus of belief, in addition to obeying three principles. The principle of success, which is to add the new information to the corpus of belief. The principle of minimal change, that says that the corpus of belief should be changed as little as possible, and principle of no contradiction, since it is granted that the corpus of belief that is obtained must be coherent from the logical point of view. Thus, in general, we will think that this chain called revision of belief is represented by a circle operator, where L is the set of formulas of a propositional language, phi represents the corpus of belief, alpha represents the new information, and we will call phi circle alpha to the new corpus of belief. This view that the formula represents people belief is the idea of Katsuno and Mendelssohn, and it is a simple way of looking at the revision. The logical model of revision of beliefs proposed by Theorem, Gardeford, and Michelson characterizes the revision operator by postulates, and with the language considered is finite, this model coincides with that of Katsuno-Mendelssohn. Thus, according to Katsuno-Mendelssohn, an operator if or revision, if it satisfies the six postulates present here. R1, relative success, says that models in the revision are alpha model. R2, economics express that if phi and alpha share models, then the model in the revision coincide with the conjunction. R3, consistency. R4, independence of syntax. R5 and R6 some way capture minimality and change. Moreover, capture the fact that an operator can be characterized by a ranking order. A ranking order is the strict relation associated with a total preorder. And a total preorder is a binary relation that is total and transitive. Now, there are two ways to capture the revision. The one we just saw say that postulate must satisfy the function, and the other that is the structural way of defining the operator. For this, it's necessary to define a faithful assignment. A faithful assignment is a function that maps each formula phi into relation such that the relation is a ranking order and the minimal model of the relation are exactly the model of phi. Based on this definition, Katsuno and Mendelssohn create a representation theorem for their revision that say the operator satisfied from the postulate from R1 to R6 if and only if there is a single faithful assignment such that the model in the review are exactly the minimal alpha model according to the ranking order. The following figure illustrates this representation theorem for the revision. Note that the ranking order is represented by the parallel lines. If two models are on different lines, the one below is considered less than the other, The models that are in the same lane are not compared. Alpha review model are indicated in black. The model in the lower line are the most plausible model for phi. This is a simple way to present the revision of belief. However, there are others. For example, the concentric effect of growth. In general, representation theorem relates postulate with structure that in some way represents knowledge and its change. The theorem of representation of the revision are important because they give an idea that beliefs are organized in concentric spheres, and therefore an order structure is captured in some way. This order structure are binary relations defined of a finite set of interpretation, and among we have partial order, which is an unreflective and transitive relation. In the figure, we can see an example of this. The partial mean order is a relation that satisfies the following property. If omega is a minimal element, okay, and omega prime is not a minimal element, then omega is minor than omega prime or is below omega prime. That is, a minimal element is always less than one that is not a minimal element. An example of this is presented in the figure. Note that those that do not have model below are the minimal elements. This and this. The ranking order coincides with the strict relation of the total preorder, and where the symbol, that is, also called indifference, indicates that omega 1 and omega 2 are not related in some way. We say that the relation is a semi-order if it satisfies the following three properties. SO1, the relation is a non-reflective. SO2, if three models meet the relation, any other model greater than 1 or lesser than omega 3. If omega 1 is less than omega 2 and omega 3 is less than omega 4, then omega 1 is less than omega 4 or omega 3 is less than omega 2. An example of a semi-order is represented in the figure. Sorry. We also define a main semi-order where the relation is a semi-order in each element that is the minimal is less than those that are not minimal. A typical way to define the semi-order is as a function of range and a threshold. That is, the relation is a semi-order if there is a real function that we can see as a function of preference and a non-negative constant q, such like omega prime is preferred to omega if the score given to omega prime exceeds the score given to omega by exceeding the threshold. The following graph illustrates the representation of a semi-order with constant threshold q equal to 1. And the function is defined on the right side. For example, between omega 3 and omega 5, the difference in score is less than 1. That means that there is not a relation between them. However, between omega 3 and omega 4, the difference in the score exceeds the constant value 1. Therefore, exists a relation And in this case, omega 4 is less than omega 3. Note that every semi-order can be represented in this way. Now, we have new structure. The question that arises is, what postulate correspond to those order structure to obtain representation theorems? This is because one may think that the AGN revision theorems correspond to a type of representation where the way to revise corresponds to that order structure, which is of total preorder. But that is very particular way of representing preference over work. There are other ways of representing preference that are not given in such a strong way, such as total preorder. For these types of structure present, there are also adequate representation theorems and postulate that capture this type of change. But first, it's necessary to define the assignments. An assignment is the semantic way of capturing how the information is going to be changed. That is, the revision from a practical point of view. Thus, we define an assignment as a function that sends a formula in an order relation that satisfies the following properties. Since we have considered a structure where there are no cycles, there will always be minimal elements. And the minimal model of the relation are exactly the model of phi. We present different types of structures. Now, we are going to have different types of assignments. Here. The first correspond to the classical Katsuno-Mendelssohn representation theorems given at the beginning. The second also corresponds to Katsuno-Mendelssohn fourth Bohr partial orders. The third corresponds to Benferrat, Lagrue, and Papini. The fourth corresponds to Pepas-Williams, both for semi-orders. And the fifth is ours. The next postulate corresponds to the presented structures. Note that the postulate R1, R2, 3, and 4, and 5, and R6 correspond to the Katsuno-Mendelssohn revision theorems in the case of strict total preorders. The postulate 2' and R7 until 10 are needed for the other structure. Some subsets of these postulates correspond to some revision operators. In the following table, we present a summary where the revision operators are defined with the associated structure and the corresponding postulates. The first corresponds to the classic representation of Katsuno-Mendelssohn. On the other hand, the operator is called PKM revision if it satisfies the postulate from R1 to R5 and R7, R8. The associated structure is the mean partial orders. The operator is called P revision if it satisfies the postulate of PKM revision by replacing R2 with R2 prime. The associated structure is the partial orders. The operator is called SOPW revision if it satisfies the postulates from R1 to R5 and from A to 10. The associated structure is the mean semi-order. The operator is called SO revision if it satisfies the postulate of SOPW revision by replacing R2 with R2 prime. The associated structure is the semi-order. Here's the postulates. Finally, we have T-appropriate representation theorems to capture the change with the new structures. Note that the statement is similar to the classical theorem present at the beginning, the Katsuno-Mendelssohn classical, only that the type of revision operation and the structure associated with the faithful assignment are suitable. Final remarks. The form of structuring the preference is considered as way in which it is going to be reviewed and has been described with the different revision operators. The different kinds of assignment are shown in a simple way. In the work, we present in a uniform and simplified way the proof of the 5 representation theorems and the natural relation between a structure given a hierarchy between the classes of revision operator through the representation theorems. This last point can be illustrated in the following figure. The arrow indicates that every revision operator is an SOPW revision operators because the ranking order is a particular type of mean semi-order when the threshold or value of the constant is 0. Every SOPW revision operator is a PKM revision operator and is O revision operator. And these are P revision operator. This means that the P revision operator are the most general and the revision operators is the most restrictive. This is all. Thanks for your attention.